Good day, viewers. You are welcome back to Tindanious Maths and Science tutorials. If you are new here, kindly subscribe, share, like, and comment for more interesting and catchy videos. Today, we are going to consider Euler's form or exponential form. Let's do a little bit of recap over here. We said there are three ways of representing complex numbers. One, we have the rectangular form or the Cartesian form. Number two, we have the polar form or the circular form. And the third one, we have the Euler's form or the exponential form. And from our previous lectures, we learned on how to convert complex numbers from rectangular form to the polar form and to the exponential or the Euler's form. And we also learned on how to convert complex numbers from the circular or the polar form back to the rectangular or the Cartesian form. So if you are new here, kindly visit my previous lectures where I've dealt with that into details. For today's session, we are going to treat exponential or the Euler's formula. Now, we said that for complex number z, to represent complex number z in the rectangular or the Cartesian form, it takes this form: a plus ib, and this is the same as x plus y. So this is what? The rectangular form of representing complex numbers. And to represent complex numbers z in the polar or circular form, we have the modulus r. Multiplying, we have the cos theta plus I sine theta, where theta is the true angle, where theta is the argument, where theta is the amplitude. If you want to appreciate this, kindly visit my previous lectures where I've dealt with the Argand diagram or the complex plane into details. So this is the polar form of converting complex numbers. And the last time we have complex number z in the exponential form, we have r multiplying e to the power I theta. Okay, so this is the Euler's form, okay, the Euler's form or the exponential form. So r equals r. So therefore, I can say that e to the power negative I is equal to this expression. So note this. I say that e to the power I theta is equal to what? Cos theta then plus I sine theta this way. Again, e to the power I pi, okay, or pi I is equal to -1. So let us appreciate questions regarding Euler's. Okay, viewers, let's solve this. Express complex number z equals 10 over 10 plus 5i over 5 in the exponential form. Okay, so we have z which is equal to 10 over 10 plus 5i over 5. This is the same as 10 cancels 10, 1. Then plus 5 cancels 5, 1. Then we have what? I. Okay. So let's look for the modulus r. The modulus r is given by you square the real number part, 1 square then plus 1 here, okay, the imaginary part square, okay. So we have 1 square. This is the same as what? 1 plus 1. So therefore, my modulus R is equal to square root of what? Of 2. Now let's look for the angle theta. So you have theta is equal to tan inverse of the imaginary part over the real part. So this is the imaginary part, which is what we have 1, okay? So I have 1 over 1. So this is the same as tan inverse of 1. So theta is equal to tan inverse of 1 in radian is equal to 1 over 4 pi, or pi on 4 radian, okay? Now, so in the exponential or the Euler's form, you know that z is equal to r times e to the power I what? Theta, okay? R is what? Is root 2. Then e to the power, then I times theta is what? Is 1 over 4 pi. So which is equal to square root of 2, and you have e to the power what? You have 1 over 4 pi what? I. So this is the solution. So this is how to change a complex number from a rectangular form to the exponential or the Euler's form, as simple as that. Now let's learn, okay, so if you know the format or the way to change complex numbers from rectangular to exponential, let's also learn on how to change exponential complex numbers from the exponential form, something like this nature, back to the rectangular form. So let's do that by solving questions to throw more light on this. We have express this time around. You have your complex number in the exponential form and you want to convert it to the rectangular form. This is the same as a plus I b, okay? So we have e to the power 1 on 2, then pi what? I. Viewers, remember that we said e to the power I theta is the same as what? Cos theta plus I sine theta, okay? So this is the same as I have cos. So cos, sort of the theta, I have this. So I have 1 on 2 pi. Then plus I over here, I, then sine theta, okay? But the theta here is what? We have 1 on 2, then you have pi this way. Now, permit me to work in radians, okay? You can work in degrees, all right? So cos of 1 on 2 pi in radian gives 0. Then plus, you have I, then sine of 1 on 2 pi gives 1. So this is the same as what? 0 plus I, which is equal to what? I. So therefore, e to the power 1 on 2 pi I is the same as what? I in the rectangular form. So when you have it this way, this is what it means. Consider that the whole of this is x, okay, and the whole of this is what? Is y. So from here, so you have the imaginary part, which is my y here, and you have the real part, which is my x here. So you add x plus y. This is x plus y, x plus y. We have this as simple as that. Let's solve the second question. So let's consider this question. Express z is equal to 2 times e to the power negative 1 on 3 pi I in the rectangular form. Okay, so we have this. Okay, z is equal to this, but we know that e the power negative 1 on 3 pi I is the same as what? Cos then of the angle. We have what? Negative 1 on 3 pi. Then plus I sine, and have what? Negative 1 on 3 pi. This way. And 2 is multiplying the whole of this. So I can say 2 e to the power negative 1 on 3 pi I is the same as what? So I'll just multiply the whole of this expression by 2. And I say 2 multiplying, we have cos, we have negative 1 on 3 pi, then plus I sine negative 1 on 3 pi. This way. Okay. So now I can say that this is my x, this is my y. Okay, so I can say that x is equal to cos, I have negative 1 on 3 pi. I can also say y is equal to this. Y is equal to sine, I have negative 1 on 3 pi. This way. So again, permit me to work in radian. So in radian, I have cos, then I have negative 1 on 3 times radian, and I'm getting half 1 on 2. Then y is equal to, for this, I have in radian, I have negative 1 on 3 times radian, and I'm getting negative root 3 on 2. Okay, so therefore, so in the form x plus iy, so I can say that we have 1 on 2, which is x, then plus iy. What is my y? This is my y, and y is equal to this. So I have y, I have negative root 3 on 2. This way, is that also? So I can say that this expression is the half. Then the whole of this, which is the y, is equal to this. And this is the I, and this is the expression. Multiplying 2, you can see 2 here. So this is multiplying what? This is multiplying 2. So 2 multiplies this, and 2 multiplies what? That. So I can say 2 times 1 on 2 plus, I have 2 times I times negative root 3 on 2. So 2 cancels 2. 2 cancels 2. So I have a complex number z, which is equal to 1. Then I have negative, then I root 3. And this is the same as what? 1 minus root 3i. Viewers, this is the end of the lesson. So far as Tindanious maths and science tutorial is concerned, we are going to learn a lot. Alright? I want to throw more light on something over here. For the first question here, we found for the angle. Okay? The real part is positive and the imaginary part is positive. So we are working within the first quadrant. And in the first quadrant, theta is equal to alpha. So whatever angle you have over there is your true angle. Other than that, you need to employ the Argand's diagram to proceed from there. because this angle may not be the true angle unless we test using the Argand diagram. If this is your first time, kindly visit my previous lectures where I've dealt with Argand diagram into details. The name of the scientist who proposed the Argand diagram is there. The year in which it was proposed, okay, the year is also there. The applications of Argand diagram is also there. You can even apply Argand diagram in electrical and electronics engineering. Just visit my previous lectures on that and you'll be fine. My next interesting topic regarding this topic, okay, is de Moivre's theorem. At times you can be given complex numbers raised to a certain power, and that power at times is extremely high, not 2, not 3. It can be, let's say, to an exponent of, let's say, 10, 12, 11, 8, 9. Would you want to employ the normal way of doing things? Not at all. So meet me in the subsequent lectures where we will deal with that using de Moivre's theorem. Bye.